Hello students, I welcome you all to basic bioelectronic class 3. Previously we have some basic properties of semiconductor materials, especially the bonding concept associated with semiconductor material. The concept of intrinsic and extrinsic semiconductors, charge concentration in intrinsic semiconductor, as well as charge concentration in extrinsic semiconductors. Also referring to carrier motions in semiconductors, we have come to know that there are three types of basic carrier motion processes: drift, diffusion, and mass action law. We now want to show that how these properties are applicable to a biological medium. But you should remember one thing, that whatever the properties we have earlier discussed, those are associated with a solid phase, say semiconductor material. But now we are moving from a solid phase to a liquid phase as far as biological medium is concerned. And as far as biological medium is concerned, system is concerned, the typical habitat of biological systems is made of electrolyte solutions, that is water solutions containing ions as solutes. As far as one single molecule is concerned, for example, say one water molecule, two hydrogen atoms and one oxygen atom combine to form a water molecule with covalent bond. Water molecule is a dipole, whereas one water molecule binds with another water molecule through dipole interaction, which is a type of physical bond commonly known as hydrogen bonds. In physical bonds, such as ionic bonds, an electron is completely transferred from one atom to another of a different element, forming charged particles called ions. Such bonds are formed between highly electronegative and highly electropositive elements. For example, in the formation of bond between sodium and chlorine, the sodium atom loses an electron and becomes a sodium ion, and chlorine atom gains one electron and becomes a chloride ion. These resulting ions exert an electrostatic attraction and enter into a bond formation. Due to the presence of neutral molecules, different ions, charged macromolecules, dipoles, etc., we get different types of bonds in a biological medium. Say for example, covalent bond, for example, bond between hydrogen and oxygen in one water molecule. Ion-ion interactions, say for example, sodium and chlorine ions attraction to form sodium chloride, which is a physical bond. That is actually application of Coulomb's law. Ion-dipole interactions, say for example, interaction between a sodium ion and a water dipole, which is a physical bond. Dipole-dipole interactions, for example, say one water dipole bonds with another water dipole through a physical bond known as hydrogen bond. So in biological medium, we will get a variety of bonds. both covalent bond and physical bond. But in semiconductor material, we will get only covalent bond. That is, but still, the bonding concept, which is available in semiconductor material, is also available in biological medium. And since there are different type of interactions, say for example covalent bond, ion interactions, ion dipole interaction, dipole interactions. So covalent bond, the concept has also already been discussed in semiconductor material, referring to ion interactions. Let us see what is the energy between two ions. The interaction energy between two ions, suppose one sodium ion and one chlorine ion. What is the interaction energy between these two ions? That energy is given by equation 3.1. This one. E are equal to minus Z1 Z2 Q square divided by 4 pi epsilon naught epsilon r and capital R. This expression has been derived using Coulomb's law, because the Coulomb force between two ions we know, where Q equal to ZQ, and that is for first ion. Suppose the Q equal to Z1Q. For the second ion, Z2Q. Z is the valency of the ion carrying elementary charge Q. Epsilon naught is the permittivity of vacuum, and epsilon r is the relative permittivity of the medium. Capital R is the distance between the two charges Z1Q and Z2Q. Referring to one ion and one dipole, the interaction energy is given by this expression. This also has been derived by using Coulomb's law. This figure depicts the interaction between an ion Q and a dipole U equal to QdL, where U is the dipole moment and L is the distance between the two ions, plus QD and minus QD, forming a dipole. Suppose this is a water dipole, suppose, and this is an ion, sodium ion, suppose this one, and this is a water dipole. The interaction energy between this water dipole and suppose sodium ion is given by equation 3.2, where theta is depicted as shown. R equal to OM, the segment, this one, and AB, the length of AB, length of this dipole is L. So a distinct energy expression is available, important from engineering point of view. Dipole interaction. Suppose one water molecule whose dipole moment is U1, and another water molecule whose dipole moment is suppose U2. They will combine by physical bond or hydrogen bond. The interaction energy between these two dipole is given by equation 3.3, where theta 1, theta 2 are depicted in this figure. This one is theta 2, this one is theta 1, and this angle is phi. Some two problems are given, you will solve yourselves. Suppose problem number 3.1. In a medium of relative permittivity epsilon r equal to 80, a dipole with L equal to 0.2 nanometer and a charge equal to 0.5 q is at a distance r equal to 1 nanometer from a monovalent cation. Calculate the interaction energy for theta equal to 0 degree and theta equal to 90 degree, given q value, epsilon naught value. Similarly, problem number 3.2. You can solve this using equations this 3.2. Now let us see what is actually intrinsic biological medium, because we are actually going to show the analogy between biological medium and semiconductor medium, because both mediums or both phases are to be interfaced. Unless and until there exists some sort of analogy, especially referring to their properties, both mediums cannot be interfaced. That is why this study is required. So intrinsic concept available in semiconductor medium, we have already come to know. Let us see how this can be transformed, or this can be applied in case of biological medium. Suppose consider one water medium. Also assume that at room temperature, a small fraction of these dipolar molecules be thermally ionized according to generation recombination scheme. H2O dissociates to hydrogen ion and hydroxyl ion as shown in equation 3.4. These square brackets indicate concentrations, that is molarity, that is how much moles per liter. And if this scheme, basically a chemical scheme, this scheme is such that under standard conditions, H plus OS minus equal to 10 to the power minus 14 mole square. That is, hydrogen ion concentration is equal to hydroxyl ion concentration equal to 10 to the power 7 minus 7 mole, 3.5. Then this considered medium, water medium, is regarded as the intrinsic biological medium. In logarithmic form, this actually in logarithmic form, this equation 3.5 can be written as minus log to the base 10 hydrogen ion concentration equal to 7, or pH equal to 7, where pH equal to minus log to the base 10 hydrogen ion concentration, equation 3.6. That is the definition of pH. So basically we are considering one biological medium which will be called intrinsic if its pH value is 7. Now come to extrinsic biological medium. An intrinsic biological medium now can be made extrinsic by adding acid or base to the intrinsic biological medium. It is because acid is a substance that donates protons and base is a substance that accepts protons. Suppose now we want to find the pH of a Y mole solution of hydrochloric acid. Generally, how this solution is prepared? It is prepared by adding Y moles hydrochloric acid per liter of intrinsic water medium. Therefore, intrinsic concentration is 10 to the power minus 7, which is analogous to Ni of semiconductor discussed in equation 2.1. That is we have discussed it in the previous class. Due to addition of acid, the hydrogen ion concentration, that is square bracket H plus, will now shift to a new value, say X, which is also analogous to Nn of equation 2.3. Thus, proceeding exactly like N-type semiconductor, we get the following quadratic equation 3.7. X squared minus yx minus 10 to the power minus 14 equal to 0, which is analogous to the quadratic equation n squared minus ndnn minus ni squared equal to 0, equation 2.3 discussed in the previous lecture. Now solving for x, this one, we get this expression. X equal to y by 2 plus y square by 4 plus 10 to the power minus 14 root over equation 3.8. Again, suppose now you want to find the pH of a Y mole solution of potassium hydroxide. It is now base. This solution, exactly as previous, is prepared by adding Y moles of potassium hydroxide per liter of intrinsic water medium. Therefore, here also intrinsic concentration is 10 to the power minus 7, analogous to Ni of semiconductor discussed in equation 2.1. And due to addition of base, hydroxyl ion concentration will shift to a new value, say Z. But previously it was hydrogen ion concentration, shifting of hydrogen ion concentration. Now it will be shifting of hydroxyl ion concentration. Z analogous to Pp of equation 2.45 discussed in the previous class. Thus, proceeding exactly like P-type semiconductor, we get the following quadratic equation 3.9, which is analogous to the quadratic equation 2.5. Now solving for Z, that is Z equal to hydroxyl ion concentration, nu, we get equation 3.10. So nu hydrogen ion concentration, this is the Z is the actually hydroxyl ion concentration. For determination of pH value, we need to find the hydrogen ion concentration. So new hydrogen ion concentration can now be determined by equation 3.11. That is, this expression you have to use hydrogen ion concentration into hydroxyl ion, new hydroxyl ion concentration equal to 10 to the power minus 14. From where the new hydroxyl ion concentration Z can be determined from using equation 3.10, and from here you can determine the value of hydrogen ion concentration. Then by using the definition of pH, we can get the pH value of Y mole solution of potassium hydroxide. Say for example, one example, find the pH of a 10 to the power minus 8 mole solution of hydrochloric acid. Let X be the hydrogen ion concentration. Using equation 3.7, we get this. Now solving for X, we will get X value. That is a new hydrogen ion concentration. Thus X equal to hydrogen ion concentration equal to this mass of mole, and using the definition of pH of the solution will be 6.98. Similarly, you solve these equations. What is the pH of a 10 to the power minus 8 mole solution of potassium hydroxide? It is this, but here it was acid. Similarly, you solve problem 3.3. pH of arterial blood is measured by pH electrode and found to be 7.4. What is the hydrogen ion concentration of arterial blood? Very frequently used two terms, that one is pH buffer solution and ionic strength. What is pH buffer? A pH buffer is a substance or a mixture of substances that allows a solution to maintain a near constant pH upon the addition of small amount of hydrogen ion or hydroxyl ions to it. Conjugate acid, that is basically weak acid such as acetic acid, and conjugate base, basically weak base such as amines, can form pH buffer solutions. Amino acids and proteins are examples of biological buffers. Due to presence of this type of acids and proteins, actually more or less in our body, the pH remains constant. Ionic strength. The ionic strength of an electrolyte solution is defined as this by this expression: I equal to half summation of I equal to 1 to n Ci Zi square, where Ci is the concentration of the ith ion, Zi is the valency, and the summation extends this summation over all the ions present in the solution. It is thus obvious from this expression that the ionic strength is a property of the solution and is not the property of any particular ion in the solution. Only the net charge of an ion is used in calculating ionic strength. As a matter of fact, unionized compound such as weak acid or a dipole compound does not contribute toward the ionic strength of a solution. Now, from the subject point of view, some biological materials have importance in bioelectronics. Say for example, probably you have heard the name of protein chip or protein sensor, DNA sensor or DNA chip. Those are now well known for all of us. At least we have heard the name. So, referring to that, and also from bioelectronics point of view, you are supposed to have some sort of, at least some sort of basic knowledge on biological materials such as proteins, deoxyribonucleic acid DNA, ribonucleic acid RNA, cell membrane, eukaryotic cell, etc. These topics you may see from any modern biology book and have been kept reserved for your self-study. Thank you.